heard nothing, so. I don't think Isaac is going to need a whole lot of introduction to this room, but we've been thrilled to have him in the math program. I'm sure you've been thrilled to have him in the honors program, and I've heard some of this, and I'm really looking forward to it. Let me just pray for you. Father, thank you for your love for us. Thank you for your love for Isaac, your plans for him. Thank you for this culmination of a lot of hard working and a lot of deep thinking that Isaac's been doing, and thanks for his excitement to present this to us and to everyone he meets. And ask that you be with him, that you'd calm nerves, that you would help him to think clearly and present clearly, and that you'd be honored. In your son's name, amen.
Amen. Welcome, everyone. Thank you so much for coming. I really appreciate all of your continued support throughout this whole process, this whole journey. It's been a lot, and it's meant so much to have you all here every step of the way. The title of my work is Consistent Faith, and I'm going to be presenting on Kurt Gödel's incompleteness theorems and the role of faith in mathematics. Now, I want to open with a prompt, and I want you to just fill this in. When I hear mathematics, the first word that comes to mind is what? Give me some words.
Numbers.
Numbers? Yeah, you don't have to raise your hand.
Fear.
Okay. That.
Hard.
Fair.
Facts.
Facts, yes.
Discovered, not created.
Discovery, that's 3 words, but okay.
Things I'm bad at.
All right. Good, very good. Well, for me, more and more, when I think of mathematics, the word that comes to my mind is faith. Now, that's strange, right? Because, we heard the word facts in here, right? Numbers. It's very, concrete. There's certitude here. Why would we need faith in a mathematical, empirical system? Well, I've come to this conclusion more and more as I've studied the incompleteness theorems. And the conclusion that I've come to is that Gödel's incompleteness theorems imply that atheistic belief in the consistency of mathematics is a blind leap of faith, rendering atheistic mathematics intellectually untenable. Now, let me unpack this a little bit. The consistency of mathematics essentially just means the inability to prove contradiction, right? So I couldn't take this marker and this whiteboard and write down a valid proof that 0 equals 1, right? Because we're working in a consistent system here. And for reasons that I'll show from these theorems, believing in that consistency from an atheistic standpoint, from material first principles, it doesn't follow. And that is thanks to the work of this fellow. Kurt Gödel, an Austrian mathematician, was born in 1906, and his birthday is actually in 5 days, so you can celebrate if you would like. And he proved the incompleteness theorems in 1930. And the incompleteness theorems are 2 in number, and they go like this. The first incompleteness theorem states that within any formal system capable of expressing arithmetic, there exist statements that are true and yet unprovable from within that system. So it's called the incompleteness theorem because a formal system that has statements that are true and unprovable is called incomplete. And I'll unpack what a formal system is once we get to the proof of this. But yeah, within any system capable of expressing arithmetic, there are true statements that you can't prove using the vocabulary and the rules of that system. Gödel put it this way. One can even give examples of propositions, and in fact, of those of the type of Goldbach or Fermat, that, while potentially true, are unprovable in the formal system of mathematics. Now, when he says of the type of Goldbach or Fermat, he means mathematical questions that have to do with just the counting numbers, right? And like multiplication and addition, those sorts of things. So it's not like the incompleteness of a system is sequestered away in the most complex and inaccessible part of it. It affects the system even down at the arithmetical level, right? So it filters all the way through. And the second incompleteness theorem states that the proof of the consistency of any formal system capable of expressing arithmetic cannot be constructed from within that system. So, given a certain system capable of doing mathematics, I could not write a proof inside it, no one could, that that statement, that system is consistent. Now, you can prove the consistency of one system using another, and you'll be happy to know arithmetic has been proven consistent. That's good. But even the system that was used for that itself is susceptible to this. So, it just, again, it affects mathematics at just a fundamental level. So, now that we've made these statements, we can start to get into the proof of the incompleteness theorems, and we'll start with the first. And we're going to start with something called Gödel numbering. Before I get to Gödel numbering, though, let's ask, what is a formal system? A formal system consists of three things. It has an alphabet of symbols, rules for determining which combinations of symbols form well-formed formulas, and rules of inference for getting from one well-formed formula to another to another. To give an example of this, we can take the mathematical system that we all know and love, or don't. It has an alphabet of symbols, 0, 1, 2, the rest of the numbers, plus, minus, times, etc. So we have an alphabet. We have rules for which statements are well-formed. So for instance, this is a well-formed formula, but this is not, right? This doesn't mean anything. This isn't a mathematical statement. And then we also have rules of inference. So for instance, from this well-formed formula, I can derive this one. And I can derive this one. So the point of on purpose constructing this formal system of embedding mathematics into logic was, the aim of that was to make the process of gathering mathematical truth a purely combinatoric exercise. So it'd be a purely a process of, you take your alphabet and you select a few well-formed formulas as the axioms, and then you just apply the rules of inference over and over and over and over and get all the formulas that you can. And the hope was that that process would get you all of the true statements in mathematics. And Gödel proved that that's impossible. And he did so by constructing a bridge between logic and mathematics. And he did so by means of Gödel numbering. The first thing he did was he took the alphabet, right? You'll see that in this formal system, there are arithmetical symbols like 0 and equals. Successor of just means plus 1, so S0 would be 1, SS0 would be 2, etc. And then you have logical symbols like not, or, for all, there exists, and stuff like that. That's how he made the bridge between the alphabet and math. Now we need to get to the well-formed formulas. And in order to get there, he employed the fundamental theorem of arithmetic, which states that every number greater than 1 has a unique prime factorization. So essentially, that every number greater than 1 is a product of primes in a unique way. And primes are just numbers that are only divisible by 1 in themselves. So using that, he's able to take statements and take their numbers and build unique numbers that correspond to these statements in a way similar to this. The statement 0 equals 0. 0 is 1 and equals is 3. So that will be 1, 3, 1. So we take these numbers and we raise consecutive primes to these numbers. And we get 2 to the first power times 3 to the third power times 5 to the first power, which is 270. 270, by the fundamental theorem of arithmetic, is the only number that corresponds to 0 equals 0. And 0 equals 0 is the only statement that corresponds to 270. The one-to-one correspondence here is crucial for this bridge. It is absolutely necessary. 0 equals S0, or 0 equals 1, is a false statement, but it too has a Gödel number of 2 to the first times 3 cubed times 5 squared times 7, which is 9450. And then there are numbers that don't have statements attached to them, such as 4096, which is 2 to the 12. If you'll recall, this keeps turning off. Oh my goodness. Boop. Okay, nothing happened. There is no 12th symbol on this table, so 4096 doesn't apply to anything. So we have our alphabet, and we have our well-formed formulas. What about our rules of inference? What if we want to Gödel number something like this? This is a proof. It's a rather simple proof, given that this is one of our axioms. But it's a proof nonetheless. Essentially, this first statement says that there does not exist an x such that 0 is the successor of x. Right? In this system, we don't deal with the natural numbers. We only have the numbers 0, 1, 2, so on and so forth. From this, we can use one of the rules of inference and plug in 0 for that x and say that 0 is not the successor of 0. Now, do we just have to take these two well-formed formulas separately and Gödel number them and consider them by themselves? Well, that can be done, but the Gödel numbering is a lot more potent and has the capabilities that we need if we can put the entire proof into a number. And if you'll recall, back on my table, I'm not going to flip back to it because we all saw what happened last time I tried that. I had this line break assigned to 0. So this entire proof has a Gödel number, and its prime factorization is this. Now, this is a large number. I think it goes without saying. It has 101 digits, fun fact, but it has all of the meaning that we require from that proof. So, with Gödel numbering set up, we can now start to construct an unprovable statement. And we're going to start by taking aim at provability. The statement that we're trying to construct is going to have this meaning. I am not provable within this system. And there are two difficult words in this statement. I and provable. Within the system is given just since we're in the system. And not is, that's just one of our symbols, right? So the first word we're going to look at here is provable. And it turns out that, essentially, given any property of numbers, if you can write a test for that property in what essentially amounts to computer code with no unbounded loops, then you can write a test for that property within the formal system. So, for instance, let's think about the C test, where C of x yields true if the number x has 2 or more prime factors. C of 168 is true because 168 is 2 cubed times 3 times 7. C of 257 is false because 257 is a prime number, therefore it only has 1 prime factor. And C of 1 is also false because 1 doesn't have any prime factors. It's neither prime nor composite. Same thing for like decimals and negatives. It turns out there's another property of numbers that we can write this test for. And bringing our Gödel numbering to bear, the provability of a statement is one such property, because that statement, remember, we can Gödel number entire proofs, and we can test for the provability of a statement with such a computer program that I described before. So let's think about the B test, where B stands for the German word for provable, Beweisbar. B of 270 is true, because 270 corresponds to 0 equals 0. B of 9450 is false, because that number corresponds to 0 equals S0, which is 0 equals 1, which is a false statement, not provable. And B of 4096 is also false because 4096 doesn't correspond to any statement at all. So, with this test, we're able to access that provability that we need. So the next step is taking care of that I and putting in some self-reference here. So, how are we going to access this concept? The concept of I is a really complicated one. And Gödel was able to do so by proving a specific case of what's called the diagonal lemma. The diagonal lemma states that for any property of numbers with test P of x, there exists a number k such that k is the Gödel number of the statement P of k. Now, remember, P of k and any P of x is a statement within the system. It uses the grammar and logic of the system, which means it can be Gödel numbered. And Gödel proved that there's a number that when you plug it into that system, then take the Gödel number, you get that number back. Now, this is one of the most mind-blowing and incredible parts of it. It's also one of the most complex and difficult to understand. So, I've given an example of how something like this could work. I've written a test here for a property of slides. And it states that there does not exist a slide in Isaac's presentation such that the slide has a red background and the slide is the 25th in Isaac's presentation. Now you notice that this slide is referencing a specific slide, and I assume you weren't counting, it's fine. This slide is the 25th in my presentation. So you see that the slide is talking about itself. It's subjecting this test to itself. And to make it even clearer, I've color-coded using the colors that we've used previously. The slide has a red background, that's our test, and the slide is the 26th iterated because I've had to go forward, wouldn't want to... This still is self-reference. Yeah, that's our I. So, with these two tools at our disposal, we can now construct our statement. First, we start with our B of x, which is our provability test. Then, we negate it to get unprovability. And then, all we have to do is run it through the diagonal lemma. And that gives us a statement G, which is not B of G, where G is the Gödel number of the same statement by the diagonal lemma. This is the exact statement that we're trying to construct. And it is because this is what it means. the statement which G encodes is not provable within this system. You see it? We have our self-reference and our test, meaning this is exactly what we're trying to construct. I am not provable within this system. Now, one more quick step, just to really cement things. I'm going to do a quick bifurcation, just separate a couple things. Either this G statement is provable or it's unprovable, right? Arguments could be made that it's neither true nor false, but it's meaningless. It's just something made with pencil marks on paper. But even people who would claim that, I think, would make this concession that's either provable or unprovable. If the G statement is provable, then it's false, because the statement means I am not provable. So therefore, the system is inconsistent. But we have to assume the system is consistent, otherwise it doesn't mean anything. So therefore, the statement must be unprovable, and therefore true, rendering the system incomplete. And that is Gödel's first incompleteness theorem. The main point that I want to draw out of this is that truth does not equal provability, right? Because we would expect, we see truth from proof, right? We know statements are true because we've proven them. We know the Pythagorean theorem is true because it's proven. We even know the G statement is true because of the proof I just outlined. But if every system has these unprovable statements that are true, then ultimately our powers of proof can't be the measure of truth. That can't be what funds the truth to these statements. It has to come from somewhere else. Now, the second incompleteness theorem is proof how the left column had G is provable. If it's provable, then it's false, and the system is inconsistent. We throw this column out because the system must be consistent. So therefore, if the system is consistent, G is unprovable and therefore true. But if we were to prove the system's consistency, if we were to write a proof of the system's consistency, we would be writing a proof that directly implies the G statement. So therefore, that proof must be impossible to write if G is to remain unprovable. And that is the second incompleteness theorem. And the major point that comes out of this one is that consistency is mathematically unprovable. At bottom, it cannot be fully proven from within mathematics, because you can prove the consistency of one system from another, but how will we prove this system's consistency? We can get another one, but it's this infinite regress. There's no system that stands at the back of it that is self-consistent, that can fund consistency all the way down. So where do you get it? You have to take it on faith. And I'll unpack that more. I just want to bring out these implications a little bit. I want to leave us with two questions. Just unpack this a little. If truth and provability are different, where does truth come from? It's not going to come from just fiat, right? It's not just going to come from what we say, because the proof can't always be written for these truths. And if it doesn't come from us, then it has to come from somewhere else. And it can't come from a randomly, chaotically assembled material cosmos. So the logical next conclusion I think, would be an intelligent designer, where the truth of mathematics comes from. And this gets back to my thesis statement that I made before. If consistency is mathematically unprovable, why is it treated as such a settled fact? Right? We bank our lives on mathematics. Engineers building bridges, NASA sending people to the moon. It's every day. And mathematics is treated as such a discipline of certitude and strength. The truths of mathematics, one author described them as having this godlike infallibility. So, where do we get this, if not mathematically? We could get it from induction, scientific induction, because it's always worked, and I don't mean to discount the scientific method. It's excellent. We've gotten so much from it. But if there's some inconsistency hiding in some corner of mathematics, it is going to invalidate the entire thing. And if anything is provable, nothing is, right? So, taking these two facts together, the consistency of mathematics, if it's not mathematically provable, then where do we take it? We have to take it on faith. And you can take that faith two ways. You can either take it as the blind faith of, I'm just going to believe this because it's convenient. Or you can take the faith of Hebrews 11, the assurance of things hoped for and the conviction of things not seen. We don't see the consistency of mathematics. I mean, we don't see any mathematics. As one author put, there's no number one put in a museum somewhere that mathematicians can file past awe. But we have this confidence because we know that the God who made this universe is himself consistent. He is orderly, he knows all, he's in all and through all, and I think this verse sums it up quite nicely. For by him all things were created, in heaven and on earth, visible and invisible, whether thrones or dominions or rulers or authorities, all things were created through him and for him. This includes the ground we stand on, the chairs we're sitting in, and the mathematics that made constructing this room possible. Right? So, whether you embrace mathematics or are deeply afraid of it, I hope that from this theorem and from these proofs, that mathematics itself, how we treat it, how we use it, can lead you to doxology.
Amen.
And I know it has for me so many times, and I know it will continue to do so. Thank you.
Amen. Yeah.
Any questions?
Yeah, I have one.
Yes.
So, how old were you, Isaac, or what grade level or whatever, when you first started, like, coming on to all this? When all this started to first really puzzle you or interest you?
The incompleteness theorems or mathematics in general?
Both.
Well, the incompleteness theorems I started studying a couple years ago at the request of Professor Siegenthaler, because I was originally going for one of those unprovable truths for this presentation that has to do with different sizes of infinity. But Yeah, that's a thing. But we can unpack that later. But Professor Siegenthaler recommended that I go for the incompleteness theorems because the proof is more accessible. And yeah, I just found it a joy to work through. It's been brutally difficult, but it's been excellent. Mathematics as a whole, I've always had an aptitude for. Mom can tell you that I was a grade ahead in math basically the whole way through. She just kind of let me go on the curriculum, and I just kind of went ahead. So, yeah, math has been a lifelong passion of mine. It's really ignited here. But, yeah. Isaiah.
I have a question.
Yes, Professor.
All right, you can hear me all right?
Yes, I can.
Cool. Can you give some examples of how the results, Gödel's incompleteness theorems, are commonly misunderstood by a popular mathematics audience or a popular philosophy audience, so that when we hear them, we can know that's not what Gödel was proving at all?
Absolutely. Absolutely.
You might need to repeat that for the.
The question.
So, yes, Professor Siegenthaler asked if I could give some ways that the results of this theorem are misinterpreted by a modern audience that are a far cry from the way that Gödel meant it. The main way that this is misinterpreted is people look at truth being unprovable, and they say, well, truth must be some kind of chimera then. If we can't prove truth, then we can't have truth. And therefore, truth is whatever anyone makes of it. Truth is completely relativized. And I would say that falls apart just at the fundamental level of Gödel constructed a statement that is true and unprovable. And we can see that it's true because it's self-consistent, it corresponds, and it says I'm unprovable, and it is unprovable. So, yeah, that's I would say the main way that these theorems are misconstrued and misapplied is like a champion of postmodern thought, and Gödel would disavow that in the strongest terms. Isaiah.
How do you define faith?
Ooh. Well, besides the definition I put up for Hebrews 11:1, that's a great question. Thank you. Faith is confidence in what you know to be true, even apart from solid empirical evidence. Now, we do have an evidenced and a reasoned faith. I'm not saying that we don't. But the reasoning that we oftentimes have doesn't often go far enough to go the whole way, right? And we have to take so much on faith because we have belief in things not hoped for, not seen. We believe, we hold that our Lord is coming back and taking us all with him. And the evidence we have for that is that he said so, right? We have faith in him. Yeah. Professor Mellon.
What have you learned about yourself through the process of doing the honors thesis?
Excellent question. I have learned that I don't do very well with self-guided work, but I have a way of pushing through anyway. Like, it just, I'll have something due on Friday. On Wednesday, I'll be freaking out. Isaiah has seen this many times. On Wednesday, I'll be freaking out. And then Thursday, I'll just sit down and write. and Friday I'll finish it up and send it in. It happens, it works. And I guess I've learned that perhaps I'm less resilient than I thought I was, and at the same time, I'm far more resilient than I thought I was. And I praise the Lord for that, for the opportunity to see that. Maddie.
I'm gonna butcher his name, I'm so sorry. Golder, was he a Christian or was he?
He was a Platonist. That was essentially his religion. He was a staunch Platonist, a strong Platonist. So he believed, he had some Lutheran background, and it's actually really interesting to look into his religious thought and belief, because he believed the world was intelligible. Die Welt ist vernünftig, as he said. And yeah, he believed in a lot of, I don't have much of it off the top of my head. I can follow up with you on that after refreshing my research. But he did believe in a God, and he held to some Christian tenets, but I don't believe that he was necessarily a Christian. It's hard to say though. Ultimately he knows, so, yeah. Joseph.
What is some of the atheist mathematicians' responses or to the Gödel's incompleteness theorems?
Great question. Great question.
Could I add maybe the philosophical camp he was arguing, the logical positivists or
Mhm.
formalists,
Yes.
not necessarily atheists, but
Yes,
yeah.
sure. So, a formalist response would probably go something like, we have these unprovable truths, but we still have systems that can access them, right? We know the G statement is true because of the proof, right? So even if these statements are not provable from within a certain system, they are still provable from within other systems. And we can hopefully filter that down and get all the important stuff that we need or that we would want to have, essentially, from higher systems. And in addition, if you take a system and you change, you add another axiom or change the axioms, you'll be getting a new system that may be able to prove some of those things that were once unprovable. So I think a formalist would really lean on that as well, to say that, okay, we can't perhaps generate all the truths computationally, but we can at least get most of them. And that is we can still define what truth means within this sphere. Does that answer your question? Yeah. Megan.
Do you think that since you believe faith in mathematics, do you think if you had a atheist friend who was just as knowledgeable and passionate as you about mathematics, you could possibly evangelize them using this knowledge that you've researched on Gödel?
I think so. I really do. As I was doing this research, I started to realize just how much this fell under a presuppositionalist apologetic. And how you are almost borrowing from my world in order for you to do your mathematics. Because mathematics is, consistency is mathematically unprovable. So you have to take it by faith. Your faith is blind, my faith is reasoned. You can have a reasoned faith too.
There you go.
Addie.
Given how this has formed your view of mathematics being based on faith, do you now almost view mathematics, or for you personally, doing mathematics as an act of worship? And how has it shaped the way you see doing mathematics for you personally?
Yeah, I've definitely seen a lot of the care and a lot of the the witness to himself that God has put within this discipline. And that, like I said, it leads to doxology, right? Whenever I do mathematics, this is going to be in the back of my mind. It must be. So, yeah, I think so. I can't point to like specific areas where I've made that connection outside of like this presentation. But, oh yeah, I'm positive that that's going to be a part of my mathematics now. Any others? Okay. Thanks again.